Okay, so just start whenever.
Yeah, you can start now.
Okay. Okay, good morning. Before I get into the rest of my presentation, I want to paint a little bit of a picture for you. So think about the last time that you sat at a red light or an empty intersection, watching seconds of your life tick away while absolutely no cars were coming in the opposite direction. It's incredibly frustrating, right? Standard traffic systems are broken, and today I want to show you how I wanted to fix this using artificial intelligence. So my project applies deep reinforcement learning to optimize traffic signal phases in real time. Throughout this experience and this internship, I got the opportunity to learn to generate the traffic data sets and code the replay buffer and train a deep neural network from scratch. While there were a lot of moving parts to balance, I got to this in the end allowed me to build a intelligent agent that doesn't just follow a basic timer, it actually learned how to clear the intersection itself. So right now, standard traffic lights rely on pre-timed cycles. They completely ignore real-world spikes and force vehicles to wait or completely stop at intersections just because a pre-timed clock says it's not their turn. The real danger here is when a small light faces some technical difficulties, and those minor delays can lead into propagating backwards, which turns a minor slowdown into massive traffic jams during morning and evening rush hours. Our current manual traffic system can't just adjust or shift to traffic variations like this. Fixing this creates a massive positive impact across three main areas. First, human efficiency. It helps billions of people gain back lost hours in travel, making daily commutes faster and more efficient. Second, environmental preservation. By reducing wait times and car acceleration spikes, that drastically lowers vehicle emissions, significantly dropping those car emissions. And third, economic acceleration. It optimizes delivery, making sure that delivery vehicles for companies like Amazon, Uber Eats, or DoorDash are able to get where they need to go on time and faster. In addition to that, it also makes sure that emergency response vehicles are also able to tap in and reduce unnecessary wait time. To make this work, I set up a continuous feedback loop between the AI and the intersection in SUMO. Almost like a video game constantly updating based off of a player's input, it breaks down into four main steps. Step one is the state space. The system basically takes a screenshot of the intersection model and converts that traffic data into something that the AI can actually comprehend and read. Step two is the brain. My neural network looks at that layout and calculates which light phase is absolutely the best one to turn green onto next. Step three is the execution. The simulator SUMO instantly carries out that choice and moves those cars forward based off of the decision that the brain makes. And step four is the reward. The AI gets feedback or a score based on whether it successfully cut down vehicle wait times in the end. Once it checks its score, the loop instantly resets and does the exact same thing for the next frame, getting a little bit smarter and learning a little bit more from each repetition of these four steps. Let's look inside the actual AI's brain. The core model is a convolutional network. Instead of identifying objects in a regular photo, it scans the map of the road and gives a score called a Q value into four different traffic light choices to figure out which one is the best decision to make. I also had a replay buffer, which is basically a memory bank in a way. A common issue with AI is that it gets overwhelmed if it only learns from what it did just 1 second ago. So this buffer saves all its past decisions and pulls out random batches of memory to learn from later on. Shuffling the data like this breaks repetitive patterns, which forces the AI to learn from its past mistakes rather than getting stuck in that continuous loop. But how does the AI actually see that traffic? So the environment that I constructed in SUMO actually constructs a high resolution grid around that intersection, tracking 4 key features per cell. It looks at car count to see vehicle distribution, average speed to measure the flow of the cars, queued cars to pinpoint vehicles under 0.1 meters per second to see which cars are actually like idle or stopped, and wait times to see total accumulated vehicle delay. This gives the AI a multi-layered, complete bird's eye view understanding of the road's conditions at that specific time. So moving on to slide 7. This slide includes a visual graph, which allows me to see how my AI is performing live, which I got from this website called TensorBoard. To make this happen, I used a Python library called TrackE, which links my neural network updates directly to the active SUMO model in real time. So on the bottom left, you can see an equation that I used for the exact system to grade the AI. And if you look at my TensorBoard graph on the right bottom hand, you can see exactly how the AI reacted to this reward system over 100 steps. So for the first 35 or so episodes, it was doing really well. The AI was performing exactly how I wanted to. However, right around 70 to 75, you can see that the model destabilized and kind of fell down. And this is a common hurdle in machine learning. While it means that I may need to tweak some things later on, it shows that in the beginning that the actual underlying architecture and the data pipeline are working kind of how I wanted them to and working properly. So next off, I wanted to go over some of the performance metrics that I found. A standard traffic light resulted in about 142,500 seconds of wait time and cumulative delay. Early in training, around episode 10 or so, the AI was still guessing and dropped that down to 91,000 vehicle seconds. And that's a huge decrease, which I was happy to see. But once the DQN model was fully optimized and learning a lot more than it did previously, it brought the delay down to just 39,200 vehicle seconds. That's a 72% reduction in total vehicle wait time. Looking at this timeline, phase 1 was mostly about building that foundation and the actual model in SUMO. Phase 2 was more about training the actual AI and running that simulation over and over and over again so the AI could learn more and more. And in the future, phase 3 and 4 will mostly focus on extending this control logic to multiple intersections and hopefully in the future, maybe developing even more agents. And lastly, phase 4 will introduce emergency override systems, which would be necessary in case the AI would fail. Then we would probably go back to using that original non-AI traffic system. And to wrap things up, this project demonstrates that we don't really need to rebuild physical roads to combat traffic issues and traffic backup. We just need to make our infrastructure smarter and more urban by using deep learning and AI. So that wraps up my presentation. Thank you so much for listening, and please feel free to ask any questions.